Unveiling the secrets of electromagnetism, a journey through fields and fluids. Imagine a river flowing steadily downstream. The water's movement can be described by its velocity at every point. This creates a flow pattern, a visual map of the water's journey. Now imagine invisible fields instead of water, fields that exert forces on electrically charged objects. These are electromagnetic fields, and understanding their behavior is key to unlocking the secrets of electromagnetism. Just as the velocity field describes the river's flow, electric and magnetic fields describe the forces acting upon charges. These fields are invisible, but their effects are very real. Think of a compass needle aligning with the Earth's magnetic field or a balloon sticking to the wall after being rubbed on your hair. These phenomena hint at the invisible forces at play. To understand these fields, we'll use the analogy of fluid flow. We can visualize electric and magnetic fields as streams of invisible fluid, their motion and behavior revealing the underlying principles of electromagnetism. Let's dive in and explore these concepts further. Imagining the invisible electric and magnetic fields. Electric fields are created by electric charges. Imagine a tiny particle with a property we call charge. This charge creates an electric field around it, like a sphere of influence. The closer you are to the charge, the stronger the field, and the greater the force it exerts on other charged objects. Magnetic fields, on the other hand, are created by moving electric charges. Think of a wire carrying an electric current. The moving charges within the wire produce a magnetic field that encircles the wire like an invisible ring. The stronger the current, the stronger the magnetic field. These electric and magnetic fields are not independent entities. They are intimately connected, influencing and interacting with each other. Changes in one field can create the other, leading to a beautiful dance of electromagnetic energy. To fully grasp this interplay, we'll turn to the elegant mathematical language of divergence and curl. Gauss's law, the divergence of electric fields. Imagine a water source like a spring bubbling up from the ground. The water flows outward, diverging from the source. This source is analogous to a positive electric charge. Gauss's law for electric fields tells us that the amount of electric field flowing out of a closed surface is proportional to the amount of charge enclosed within that surface. Think of a balloon inflated with air. The air inside pushes outward on the balloon surface. Similarly, electric charges push out electric field lines. If there's no charge inside the balloon, no field lines originate from within, and the net flow of electric fluid through the balloon surface is zero. This outward flow of electric field lines from a positive charge is what we call divergence. A positive divergence means the field is spreading out from a point, like water from a spring. Conversely, a negative divergence implies field lines converging towards a point, like water flowing down a drain. Gauss's law provides a powerful tool for understanding the behavior of electric fields. It tells us that electric charges act as sources and sinks for the electric field, and the divergence of the field allows us to visualize and quantify this behavior. Section 4, a magnetic mystery, Gauss's law for magnetism. In this section, we will delve into the fascinating world of magnetic fields and uncover the mysteries that Gauss's law for magnetism helps us understand. Now let's consider the curious case of magnetic fields. Magnetic fields are invisible forces that exert influence on magnetic materials and moving electric charges. They are created by moving electric charges and intrinsic magnetic moments of elementary particles. Unlike electric charges that exist in isolation, we never observe magnetic charges in isolation. This means that while we can have a single positive or negative electric charge, we cannot have a single north or south magnetic pole. Magnetic poles always come in pairs, north and south, like two sides of the same coin. This pairing is a fundamental characteristic of magnets, and it means that if you cut a magnet in half, you will still end up with two smaller magnets, each with its own north and south pole. This peculiar property has profound implications for the divergence of magnetic fields. Divergence is a measure of how much a field spreads out from a point. For magnetic fields, the divergence is always zero, which means that magnetic field lines never begin or end at a single point. Gauss's law for magnetism states that the net magnetic flux through any closed surface is always zero. This law is one of Maxwell's equations, which are the foundation of classical electromagnetism. In simpler terms, the amount of magnetic field flowing out of any closed surface is always equal to the amount flowing in. This is because magnetic field lines are continuous loops with no beginning or end. This is because magnetic field lines always form closed loops, originating from the north pole of a magnet and ending at the south pole. These loops ensure that the magnetic flux entering a closed surface is balanced by the flux exiting it. Imagine a closed surface like a sphere surrounding a bar magnet. The magnetic field lines that emerge from the north pole of the magnet will travel through space and eventually re-enter the sphere at the south pole. The magnetic field lines emerging from the north pole will eventually enter the sphere again at the south pole. This continuous loop of magnetic field lines ensures that the net magnetic flux through the sphere is zero. No matter how we draw the surface, the net flow of magnetic fluid through it will always be zero. This is a direct consequence of the fact that magnetic field lines are closed loops. This zero divergence of magnetic fields is a direct consequence of the fact that magnetic monopoles, isolated north or south poles, have never been observed. If magnetic monopoles did exist, we would see magnetic field lines starting or ending at these points, but this is not the case. It's a fundamental principle of electromagnetism, shaping the behavior of magnetic fields and their interactions with electric fields. The absence of magnetic monopoles means that magnetic fields are always solenoidal, meaning they form closed loops and have no divergence. Carl Friedrich Gauss, a brilliant mathematician and physicist, formulated this law as part of his broader work on electromagnetism. His contributions have been instrumental in shaping our understanding of magnetic fields and their properties. Gauss's law for magnetism is not just a theoretical concept, it has practical applications in various fields. For example, it is used in designing magnetic shielding, understanding the behavior of magnetic materials, and developing technologies like MRI machines. Different materials respond to magnetic fields in different ways. Ferromagnetic materials like iron can become strongly magnetized, while diamagnetic materials like copper create an opposing magnetic field when exposed to an external magnetic field. In ferromagnetic materials, the magnetic domains, small regions where the magnetic moments are aligned, can become aligned with an external magnetic field, resulting in a strong overall magnetic field. Temperature also plays a crucial role in magnetic properties. For instance, heating a ferromagnetic material above its Curie temperature will cause it to lose its magnetic properties, as the thermal energy disrupts the alignment of magnetic domains. Earth's magnetic field is another fascinating application of Gauss's law for magnetism. It protects our planet from harmful solar radiation and plays a crucial role in navigation for both humans and animals. The magnetic field lines around Earth form a protective shield, deflecting charged particles from the sun and creating phenomena like the auroras near the poles. In summary, Gauss's law for magnetism is a fundamental principle that helps us understand the behavior of magnetic fields. It tells us that magnetic field lines form closed loops, and the net magnetic flux through any closed surface is zero. This law has profound implications for both theoretical and practical applications in electromagnetism. By understanding Gauss's law for magnetism, we gain deeper insights into the nature of magnetic fields and their interactions with the world around us. This knowledge continues to drive advancements in science and technology, shaping our modern world. Section 5. Faraday's Law, the curl of electric fields. Imagine stirring a cup of tea with a spoon. The tea swirls around the spoon, forming a vortex. This swirling motion is analogous to the curl of a vector field. In electromagnetism, Faraday's law describes how a changing magnetic field creates a swirling electric field, a phenomenon known as electromagnetic induction. Consider a loop of wire placed near a moving magnet. As the magnet moves, the magnetic field through the loop changes, creating a swirling electric field that drives an electric current in the wire. This induced current, in turn, generates its own magnetic field, which opposes the change in the original magnetic field. The curl of the electric field, in this case, represents the swirling nature of the induced electric field around the changing magnetic field. The stronger the rate of change of the magnetic field, the stronger the curl of the electric field and the greater the induced current. Faraday's law is a fundamental principle underlying many technologies, from electric generators that power our homes to transformers that efficiently transmit electricity over long distances. It highlights the interconnectedness of electric and magnetic fields, showing how changes in one can induce the other. Welcome to Section 6, Ampere's Law with Maxwell's addition. Imagine you're holding a wire carrying an electric current. The current creates a magnetic field that curls around the wire, much like how water flows around a rock in a stream. Ampere's law states that the curl of the magnetic field around a closed loop is proportional to the electric current passing through the loop. But there's more. James Clerk Maxwell added a crucial piece to this puzzle: the changing electric field. Visualize a capacitor in an electric circuit. As the electric field between the capacitor plates changes, it creates a magnetic field curl, even though no current flows between the plates. This addition by Maxwell completes the symmetry in the equations of electromagnetism, linking electric and magnetic fields in a beautifully interconnected dance. This principle is foundational in understanding how electromagnetic waves, like light, propagate through space. The interplay of electric and magnetic fields driven by changes in each other enables these waves to travel vast distances, carrying energy and information across the universe.